teach in the sessions who have thought about these questions from the miner companies, and they have, after listening these 2 days, their own idea from a scientific perspective about the ones that need more discussion and that are very important. And so they want to engage with audience these questions that seem to have raised issues and that are valuable for discussion. So they're going to talk about it here. We have it on the screen here. And Simon, do you want to lead it?
Just see it. Is this working? Can people hear me?
No.
Yes, it is working. It is? Is it working?
No.
Yes.
Put it closer to you, perhaps.
Yeah. Can people hear me through this microphone?
The level might have to be boosted in the guy might have to boost the level.
This one better? No, not better either.
We'll ask the
Okay. We'll increase this, and so in the meantime, it increases.
But also, this will also give people a chance to come back inside. If anybody could give some calls. We'll start the process now anyway. With all these kinds of discussions, the intention is not for the people on the panel here to spend all the time talking, it's actually to try and get a discussion going in the audience to address things which we think are important. But sometimes it needs a little bit of focusing, at least to start with. So between us we've come up with two sets of questions. The first set, which you can see on the screen here, is related to the remote sensing aspects and some things that I've picked up during the discussion that I think perhaps need a little bit more clarification. And later on we'll go on to the surface and internal things which are on the next slide. So I'll just explain why I came up with these questions. We were originally asked to address the Asteroid Miners questions, the list, but I think there's been a really quite a good response online to these questions. I think we've mostly addressed them. So I felt it was more important to pick up on things that have come up during the discussion. Starting at the top, which seems a good place to start, this was a kind of misconception from me, that I always felt that with asteroid mining being driven by sort of commercial thoughts, that you would not want to spend the resources in going to observe an object and characterise it before actually starting the mining process. There is actually a more practical reason why this might be possible. If you're looking at very small bodies which have close approaches to the Earth and orbits very similar to the Earth, if you have a launch opportunity to go and do a prospecting mission, then you might not get actually an opportunity to launch to do mining for another 20 years. And so there may only be one launch window at a time. So I guess this is a question to the audience. Is that in your mind that you will be launching direct to do mining, and therefore we would have to be certain that the ground-based characterisation is sufficiently good that you have the kind of target you want? Or is there a more general perception that you would have to do prospecting first before you go to the first target? So that's a question to the audience. Does anybody have any answer they want to make to that?
Oh, he has one.
For planetary resources, definitely plan on doing a characterization ahead of time. But like sending a prospecting spacecraft, doing a characterization of the chemical composition and as many physical properties as we can, and then designing an asteroid mining mission around that particular target. That's our approach, anyway.
Does this work?
Can you hear?
Okay, is it working now? Better? Yeah. Okay. Thank you. This is quite important because it does have significant
repercussions on some of the later questions, which is how well you might want to characterise your target. Because this is quite a critical thing with the sorts of sizes of objects that you're talking about. The observation opportunities are very limited. So, however, you still don't want to go to the wrong type of target and learn that it's not the right one when you get there because you wasted a prospector first. So.
Can I bring something up, Simon?
Yep.
So I should have added it to this list. There were some differing opinions about how well spectroscopy was going to tell you what the asteroid was made of. And I think I heard some opinions saying don't trust it at all. It might have even been you.
I certainly said that at one point, yes. And that's the purpose of one of the lower questions down there, so we'll come to that. Yeah. Okay, we have some more answers, because we've got 3 companies, we only have 1 answer.
So I'm picking up halfway. I'm sorry, I was outside.
So we're dealing with the first question up there.
Look, let me just say this. We reserve the right to get smarter at any time and listen very carefully. But so far, on the basis of our listening and studying, our approach is a little different. And if we hear something to show that we're wrong, we'll change it in a heartbeat. Certainly, if you want 100% surety of the target you're going to before you get there, you'll send an in situ reconnaissance mission. We think a smarter strategy is to design the mining technology so that you don't have to do that. If you want 100% certainty of the physical structure and the composition, you have to send an in situ mission before. Instead, what we view is that the resource extraction business is a stochastic business. And what we need is a certain definable probability as to what the target is made of, and a technology that can handle anything essentially from a sandcastle to a monolithic block. And then it's a game of numbers to know how many mining missions we have to send out and what percentage of them have to be successful. So we just have a different approach.
Okay, any more responses to this first question?
Joel's right, there are different approaches to this. There are many different ways to design a mine on Earth. There are lots of examples of mining companies finding an ore body and spending. Sorry, can you? Yeah, finding an ore body and spending several years trying different process flow sheets to get it to work, to figure out what's actually the economic component of a polymetallic ore body and all of those kind of things. So we've done our work on process flow sheets and extraction methods and the like. It's our opinion that reconnaissance missions are important in order to narrow down the parameter space for choosing the final process flow sheets, the final extraction method. The question of how many reconnaissance missions, how much we can do from the ground, all these kind of things are dependent on exactly what you're trying to do and what you're trying to deliver and the architecture. So from our perspective, reconnaissance missions, yes.
If I can follow up your question to some of the answers. So would the reconnaissance missions be, we've decided to mine this and we're just trying to figure out the best way? Or is there the possibility that you send a reconnaissance mission and you go, this isn't happening at all? Because that will also have implications for the characterization we do from the ground.
I think, the trick, definitely, if it's a target that you're confident is mineable, you could go right to mining, or you could try. Their point of the reconnaissance mission, from I think our standpoint, is that you're not entirely certain, and even if you're certain of composition, you're not confident necessarily of how to design your equipment to perform extraction without significant complications. So the reconnaissance mission is risk reduction as much as anything, and the trick to, I think, doing that in a way that makes business sense is to have the development of your reconnaissance mission also generate saleable products for your company, and so that's what we look at.
I'll make a comment again from the terrestrial mining industry. It's nothing to spend $100 million on mining exploration, on mineral exploration work, digging holes, etc., and then decide not to build a mine, because that's why you do it. It's a de-risking exercise. If you're going to spend $1 billion to build a mine, $100 million, that's 10% of your project cost, to decide whether or not it's economic makes sense. So we look at the same kind of thing. What's the risk reduction? What do the investment community want to see? How can we beat down the risk in a demonstrable way to the point where we have sufficient confidence? So that's a stepwise process, and it depends on the risks that are seen.
So I'll add that there are different classes of reconnaissance missions, and there's such a thing as getting ground truth on remote sensing, which could be at the target that you want to mine, or it could be at a selection of targets. And once you get ground truth on remote sensing, you may not have to do reconnaissance missions afterwards. And in fact, those preliminary ground truth on remote sensing missions could be government-funded science missions, and that may be a good role for government. Having done the business analysis, one of the issues that you have is the cost of money, and another is the synodic period of these bodies. And so if I'm going to do a reconnaissance mission to a body that's a low delta V, and in order for the mission to be cost effective, it has to be a low delta V, that implies a high synodic period. That implies a lot of waiting after the reconnaissance mission, and with the cost of money, that's a bad thing. And our sense is that early mining missions may be less expensive than current reconnaissance missions. So that's just giving you a feeling for some of the calculus that we're going through.
I'd like to add just one thought to what Joel just said. It's not the comparison of the two missions, it's the cost of a mining mission multiplied by the fraction of the times that you will fail to bring back ore versus the cost of a reconnaissance mission plus the cost of waiting for the...
Yeah, that's exactly right. So if I have a mining mission that gets to a target and the target winds up being not viable, the probability of the not viable times the cost of that mining spacecraft is a probabilistic cost. It makes sense to do reconnaissance if the probabilistic cost of a failure on the mining mission is more than the reconnaissance mission. Okay? So it all comes down, anyone who looks at this deterministically is not thinking carefully. It's a stochastic process, and it's a matter of portfolio management. So what I need to do is calculate the return on investment of 6 small mining missions, and what's the probability that 4 of them are going to fail. And how do I use spectroscopy and other remote sensing to get to the point where the business proposition of those 6 missions is a winning proposition. And by the way, there's a fundamental issue in risk management, and that is you never take a completely unacceptable risk. So even if you were to fly a reconnaissance mission and think you knew the target, and if your business plan counted on the first mining mission being successful, you have what we refer to as a bad business plan. And given the probabilities of all the different ways that the mission can fail, failure due to bad target characterization is just one mode, and you have to look at it in the larger context.
But even in the scenario that you're describing, I think there's a role for reconnaissance. It's just that because when you calculate the probability of a mission not bringing back ore that's based on the scientific knowledge. And the scientific knowledge didn't mean you went to that particular asteroid, it meant you went to a number of asteroids.
Yeah, that was my previous point.
There could be reconnaissance missions going just to general asteroids to build up your knowledge so that you can make a better risk assessment.
Now, the gentleman on the board who said, don't trust spectroscopy. So
For some objects.
that's the key thing. We don't want those ones.
That's the purpose of the next question, which I'm going to come to, which is probably an appropriate point to reach that. Patrick has something to say on that.
No, I was going to, well actually maybe it's related, but say that there was what you call reconnaissance mission, because I don't think for mining and for success, having a ground truth between ground-based and in-situ observations is enough. Because again, as I always said, you need to interact with an object to know how it will behave and how it will respond mechanically in order to design your instrument. So even with a reconnaissance mission, you can, verify whether the composition is the one you want to mine, but that won't tell you how you have to design your sampling tool, because you didn't, touch the surface and try to understand how mechanically it behaves. So even if you see boulders on the surface, etc., you don't know whether they are cohesive, whether they will be extracted successfully. So I think it's a little more complicated than for the reconnaissance than just going and look whether the spectral observations from the ground are consistent with what you see in situ. So either you decide to not do reconnaissance to trust, your guess, or try to design a sampling tool that can cope with enough large kind of materials, and therefore you don't necessarily need to interact for the reconnaissance mission. Or if you want to really design your instrument to cope with the surface of this asteroid, you will anyway have to interact with it in order to know that. I think that's one of the things which is important. That's what we do for these Osiris Rex, and I help there too. They try to design a sampling tool which still is constrained to some assumptions based on thermal inertia measurements, etc. But we hope it can cope with enough large kind of material. But here we are targeting 60 grams or milligrams, so that's, let's say, easier to do. If you want to really mine bigger, then you need to have more information, I think.
Yeah, I do think it's important to recognise, though, that some of those questions are going to be answered by the science missions that maybe we hope at least 3 that happen before this kind of activity starts. So it may be that there are some what you might regard as standard properties that more or less any body of this size that's a rubble pile has, that you can tell from just doing 2 missions where you see the same thing happening again, and you perhaps don't then need to just to keep reconfirming that for every target you're going to go to. But I think that the issue about but those are things you can only test by going there. I absolutely agree. My next question was really directed at one step before that, which was what observations do you need to make from the ground to avoid the consequence of going to a target which has nothing of interest to you? And of course, it's important to think what's the minimum I need, because these things are so damn difficult to observe because they're so small and so faint, and the observing opportunities are very limited, usually at discovery, and that's it. So it's a decision about what is the minimum really diagnostic thing that you can measure that gives you a level of certainty that the target you're going to go to is one you're interested in. Is Andy Rifkin here? Yes. This I think comes down to something that you raised in your talk about targeting a CH, because you have a spectral signature for them which you can look for. If it's a low albedo or it's a sort of flat spectrum, just look for that signature. You have a CH and then you have some kind of level of certainty. However, there may not be many of them to pick from. So is that a good strategy, or is there something else? So this is a sort of question: what do you think is the minimum kind of observation that you would need in order to be as confident as you can? And certainly I would say avoid anything with an X in the classification.
Actually, I have a question for the mining industry related to that, because that will also apply. Are you interested more in a regolith-like material or in a solid-like material? Because this is linked to what kind of observation you need from the ground. Are you interested to know the thermal inertia? Are you looking for low thermal inertia, high thermal inertia, etc.?
We're interested in material that has the highest concentration of volatiles, and specifically, again, perhaps I'm not speaking loudly now. We're interested in the material that has the highest concentration of volatiles, specifically water, because that's what we see as the first product. It's also what we can use to get material back to Earth orbit. And if that means it's in the solid material, that's one of the things that we need from a reconnaissance mission. If it's in the regolith, again, we want to know that. As described, we have multiple extraction and process flow sheets. We will down select the final one when we actually know what we're going after.
Okay, that really, given that these objects are going to be so desiccated that there's not going to be free water ice, it probably doesn't matter, at least for that, whether it's a regolith or a solid. You want hydrated minerals in there, yeah.
Yeah, and I'd love to see the ground truth of that.
Yeah, okay. So there's one purpose for your reconnaissance mission, yeah. Okay. So it's still the open question then of what observations you might want to make, or you might want the people who are going to be doing those ground-based follow-up observations. What are the key things that you want to measure? Because in reality, thermal inertia is an impossible task for these tiny bodies. They're just never bright enough. But getting a light curve, a classic thing, you don't want to go to something that's spinning once a second. So that's relatively straightforward, you can do. But what compositional measurements might you want to make?
I guess I was maybe going to, this might be jumping ahead, so let me know. I think part of your question is predicated on the idea that we only have the facilities that exist now, and we only have the access to those facilities that we have now. So like I said, if I'm jumping ahead, I'm jumping ahead. But it's not impossible if companies are willing to drop tens of millions of dollars or hundreds of millions of dollars that they'd see putting up a private space telescope for their use as a reasonable investment. In that case, if you really optimize it, right, if we weren't depending on the leadings of astrophysicists, we might maybe and try to optimize if it was like, look, thermal inertia is super important, and we got to get them for these objects that maybe it's not impossible.
Yeah, okay. Yeah, I mean, it's bringing in the next question as well, which is fine. That's the two things are really quite intimately linked.
Simon, I was wondering if I could go back, and one of the things that I think is a key question for the asteroid miners that maybe even before you start at sort of level 0 is what targets are available in low delta V orbits. So identifying a target population that you may want to go after, what, sort of like your geologic map of what is out there in terms of delta V, long synodic periods, albedos, low albedos as a first cut, so that then you can fine-tune your ground-based observations or maybe low Earth orbit space-based observations on particular suites of targets. And you'd be able to identify targets that would be in near-term opportunities and maybe even far-term or near-far-term opportunities that would come around that would be available for investigation and also spacecraft missions.
Well, if you're asking me what's the population, what's the compositional distribution of the sort of bodies smaller than 100 meters, I haven't a clue, because we haven't measured them. So that's a step. Yeah, I know you know that, and that's okay. It's part of the process. But all this is predicated on the fact that there will be discoveries of objects which are, your potential targets. So, yeah.
I would point out that that's a logical way to proceed. The problem is that most of the objects we find start at 21st magnitude when they're discovered, 20th, 21st, and then the next time around, they're 5 magnitudes fainter.
I'm talking about Space Telescope Survey.
Yeah, it still doesn't help.
27th magnitude, you're not going to see it on the next apparition. With Hubble Space Telescope,
No, I'm
you
talking
can't do it.
about Hubble Space Telescope. I'm talking about infrared survey telescope.
Well, NeoCam would be a great idea, but
Right,
it's
so-
going to be very hard to see things. It doesn't see all that many things below 50 meters, as I understood it.
It sees a significant number. So
Okay.
again, it's just it's a step that I think is a foundational asset because we have the same problem for human exploration targets.
Well, I love
So-
NeoCam, right?
so-
But has Amy and Co done the work to see how bright they are on the next apparition, even when you're surveying?
You can find them well before. You don't have to worry about apparitions. You can find them early enough so that you have good opportunities later on.
That's a crucial input fact. That's very important.
So one other, I think, foundational question is, my understanding is that the 3 asteroid companies that are here, mining companies, have 3 radically different concepts of how to mine asteroids. And that would guide, a radically different choice of target bodies. Like, I understand the concepts range from grabbing a small rock and bagging it versus setting up a mining camp for long-term operations on many kilometer size body. Am I wrong about that? Yes, if there's vastly different approaches, then there's probably going to be sets of answers to this, not one set of answers.
Yeah, different approaches for sure. Going back to the original question, and not thinking about current limitations of the technology for observation, being able to look at the 2.95 micron feature, looking for hydration features, even having organics, what, 3.4, is that organics? Like, just being able to understand to what degree we can be confident in how, if it's something as a carbonaceous asteroid, so being able to look for those volatile species and put those constraints on it would be ideal for sure. I am not as familiar with something like Andy is with Earth-based or ground-based or orbit-based observation and how realistic it is to actually observe organics or something like that, but that would be a really good start for us, I think.
Yeah, if you were going for the near infrared stuff, it's really challenging, not just because of the limitations from ground-based, which I would say for the small objects is impossible. The difficulty is that if you're observing them near 1 AU, which if they're in near circular orbits they are, you also have to remove the thermal component as well, which is quite tough. So I think Marco has, you want to add to that? Yeah, okay. So that really might be quite challenging, and I think realistically for the small bodies, you'll be confined to the optical, or at least only up to maybe 2 microns, which doesn't allow you to see that hydration band directly. Certainly from the ground, it's a non-starter.
Yeah, I guess I would partially agree. I think all we can partially agree on. We have done it on AOs. It does get, it is certainly challenging for the ground. There's only a very small number we've ever done. The thermal correction is a thing, but it's doable. So I may be slightly more, or somewhat more optimistic about the idea of
for the big ones.
For the big ones, yeah, that's fair enough. I do think, like I sort of alluded but never quite said, I think that, yeah, the 0.7 micron band is probably your better bet. It's easier to observe. It is highly correlated with having the 3 micron band. So it's an easier thing to observe, and the problem would be that you're potentially limiting your object set more than you need to, and then like we were saying, it seems not to be as prevalent on NEOs as you might expect based on the main belt. So figuring out why is a science question, and you know.
Yeah, I have a comment and maybe an idea. If it works, you guys give me $1 million. The idea is the following. So you guys
give you the $1 million. Doesn't matter.
Okay, good. Then I buy telescope time and I will do the following. So the idea is that the guys you want to look after are those with low delta V, which means orbit very similar to the Earth, low inclination. And the source region of these guys are not everywhere. They're just mostly in the inner main belt. They come from the Nu 6 and they come from the 321. And there are not many families that actually produce these guys. So probably we don't need to characterize all of them. We just have to characterize their sources a little better. And then maybe with the simple observations like color or the low resolution spectroscopy, we can actually tie the object to the source region and then understand what it is. And so that's what Andy was describing yesterday, like put them in context. So there are like a few bunch of families, asteroid families producing these guys. There is like the dark ones, Polana, New Polana, Eulalia, which are compositionally very similar, for example. There is Erigone that is slightly different. Maybe Erigone is more hydrated than the other two. And then there are S-types and maybe other things. So that we still don't know very well, the LX type. So let's go find out a little better. And this is what we have to do, in my opinion.
So back to the planetary scientists, would it be a better approach to look at delta V first as like a first cut, or look at composition first as a first cut? Because it seems like we're kind of flipping back and forth between the two approaches, and I wonder if there's a straightforward, easy answer to that.
I think the answer is you do both, but what you don't do is spend a lot of time looking at very small objects that aren't in the delta V regime that you want. So you characterize the population to get as best picture as you can in the way that Marco suggested, so that you know what particular orbital group composition might have a preference for. But when you're looking for the very small ones, you just target the ones that are potential to travel to. So you use the population studies for the somewhat larger ones to build up your picture, and then focus in on the small ones which are hard to see, just for the ones that you can try and go to. But in reality, you should be doing that at discovery and not sort of waiting to see.
I wanted to add something what Marco said before. Is what I'm missing in the discussion is new data mining technologies like big data or deep learning. I mean, the problem you were referring to is that the data is not stored, or it's stored on that is not accessible, so that we cannot use such advanced technology to find patterns.
No, this is not true. The data is very public. For example, the group of Rick Binzel, they do a lot of spectroscopy on asteroids, Francesca De Meo, Christina Thomas, Nick Moskowitz, and so on. They immediately make the spectrum available to the entire community, even before publishing it.
But not the classification.
The what?
Not the classification.
The classification is the classification is, I think it's better to look at the spectrum itself. The classification is somehow misleading, but once you have a spectrum, you can classify it yourself in like a minute. So I don't see any problem there. If I can, before Andy takes it, I want to say one thing. It's kind of difficult to find this information in a quick way, because this is what we're trying to do in Nice. So we have developed like an embryon of a what we call minor planet physical properties database, where you can actually click and get the information very quickly. Because the problem is that this information, spectral videos and so on, are dispersed in many tables, databases, One is MIT, the other one is in some publication, and there's the need to collect this information, get the good ones, and put in a place where you can actually, or in the cloud or whatever, that you can access.
That's what I'm saying.
But the information is there.
Yeah, I think that it's not that the information is lost, which might be true for some of the raw data that comes out of the telescope, but as users, you're interested in the end product, the spectrum. Yeah, and it's available, but it's dispersed. That's the issue, not lost. Yeah.
So you cannot use these advanced technologies to mine.
It is not so difficult. So, for example, again, if you pay me a couple of postdocs, we can put together information in like a year or so, and then we give it to you.
Because if the information was gathered, then you can drive these advanced data mining technologies to try to find patterns, and exactly what you said. You will find automatically the patterns which are relevant for the mining business.
So the Minor Planet Center also has an embryo, or whatever you call it. But the Lowell Observatory has a grant right now from NASA to develop such a database. So I don't know the full characteristics of it, but I think it's similar to what we developed, what Marco developed. And it should go live in 2017, probably the second half.
I think from a statistical point of view it's very good. It's becoming a little tricky when you want to know the property of that particular asteroid, because the spectrum might have been observed in not good weather condition, or I don't know, the spectrum was slightly off the slit because the telescope didn't perform very well, and this is more difficult. So for example, we see it with Didymos, or whatever, Didymos, another object. When you say, are you sure this is an Ornicon-Wright? Then we observe it again, we find a slightly different spectrum. The albedo could be slightly different because maybe the albedo I derived in the first place was not derived during thermal observation in a good night conditions. These are the difficult things to do for me. But from a statistical point of view, the things work, they are there. We just have to gather in a better place.
Yeah, I'm aware of the time and the fact that we have a break, and Andy has been waiting patiently to make his next comment, so if you'd like to do that.
We moved on a little bit. I was just going to point out to Jose that the SMAS website not only has the spectra, but it does let you do the classification yourself. It has a thing you can click on, so it might not give it to you, but it gives you all the pieces for you to then run it through. And I guess I'll also amplify that I think there's a place for a kind of a big data approach for asteroids. People first were doing it with the Sloan survey data, and I'm sure they'll be doing it with Gaia, with WISE, with all of these things. So I think that a lot of the best targets, or a lot of the worst targets for mining will make themselves obvious, and then it'll be a matter of picking through the rest.
Okay, I'd like to propose that we have a break for coffee, and when we come back, very briefly address the bottom two questions on here, because we'd like to move over to the...
Yeah, so 20 minutes.